Hi there. Today we're looking at dynamic routing between capsules by Sarah Sabor, Nicholas Frost, and Geoffrey Hinton of Google Brain. This paper is a bit older, but it's made quite the impact at the time, and so we'll go through it. I find it's a pretty hard paper to read and kind of understand because a lot of things are very implicit and hand-wavy. So we'll kind of go through it and try to get the best out of it, try to explain what capsules are and what they do, and how they, stack against current networks. So, capsule network, in essence, is a new type of neural network made of capsules. And here it says a capsule is a group of neurons whose activity vector represents the instantiation parameters of a specific type of entity, such as an object or an object part. Kind of cryptic, but so what they're saying is that in a capsule network, let me try to draw one here actually. In a capsule network, you have what's called capsules. And capsules, you can imagine, as just little blobs of things, right? And they're also ordered in layers in this case. Let's actually leave away the second layer. And each of these capsules will correspond to an entity in the input. Let's say the input is an image. So somewhere here there is an image, right? Then maybe this capsule here will be responsible for detecting, is there a wall in the image? And this one will be responsible for detecting, is there a roof? And this one will be, is there a door? And this one will be responsible for detecting, is there a lake in the image, right? So now each of these capsules can, on one hand, can either be high or low. So if you imagine now a situation where wall high, roof high, door high, lake low, it means probably the image has a house on it, right? But second of all, not only can it predict whether or not a given entity is present in an image, but the individual capsules are also responsible for encoding the exact way or shape or form that this entity takes. So the wall could have different aspects such as color green. It could have size, tall. It could have orientation. Orientation is like, I don't know, vertical. Cool. And then roof could have angle, right? Angle wide. So it's a wide roof or a flat roof, right? These are kind of attributes of these things that also the capsules would encode. So ultimately, what these capsules that they are proposing will output is the roof capsule here, for example, would output a vector. So the output of the roof capsule is a, let me draw a coordinate system, is a vector. Now the length of the vector will represent, so the length, draw this norm here, will represent the probability that the roof is in the image. That there is a roof in an image, right? The roof is an element of this input image. This is simply the length. And the individual coordinates will encode these attributes. So this here, for example, this axis could be the angle of the roof, and this axis could be the color. Let's say the angle is like some degree number that can be positive or negative. Maybe a roof can be like this. Right, but in essence, this is a flat roof, and this is a very narrow angle roof. So you can imagine something like this, and then the color could also be maybe parameterized on a one-dimensional. It can have more dimensions than two. I just can't draw more. So depending on where this arrow now points, for example, this vector here has the same probability that there's a roof in the image, like if the output is this, but the color will be different. The angle will be the same because they're roughly on the same, this axis here, but the color, this will encode a different colored roof. And then if the vector is something like this, a very short vector, it will encode the same angle and color directions. So maybe I shouldn't say the position on the axis. It's more like this angle and this angle that encode the attributes. So the kind of the angular components, if you will, encode the attributes, and the length encodes the probability. So this small vector has the same direction in terms of color and angle of the roof, but it's much less probable, much less likely. So this, if the capsule outputs the little blue vector here, it says, well, if there is a roof, it's going to be this color and this angle, but I really don't think there's a roof in this image. Whereas if it outputs the large green one, then it says, oh, I'm pretty sure that there's a roof, and it's going to be this angle and this angle and this color. All right, so that is what each capsule is supposed to do. Each capsule takes the input and outputs a vector that encodes if the entity that the capsule is responsible for is present in the image, A, and B, what properties this entity has. And then we get to the point where there's the next layer of capsules. So the next layer of capsules takes information, so each capsule here takes information from each capsule in the lower layer, like you're used to from your neural network, and integrates this information. And we'll talk about how this works. It integrates all of this information, right? All of these are vectors now that come from the lower layer. Integrates all of this information. And again, each capsule in this next layer is responsible for a entity. Now, these entities in the higher layers are usually composite entities of the lower layers. So this one here could be responsible for house. This one could be responsible for national park. And this one could be responsible for beach or something like this, right? And then each of these will integrate all of this information from the lower layers and then come up with their own output vector encoding whether or not a given entity is present in the image. Of course, the house class will pick up if there is a door, a roof, and a wall in the image. The house class will pick up on that, or that's how it's meant to work. House class is meant to pick up on that and then itself output a large vector saying there's probably a house in this image. So each of these capsules by itself is responsible for encoding the presence and attributes of a object or object part or entity or part of entity in the given input data. And of course, the last layer here, it will simply be your classification layer. So in the last layer, you have as many capsules as you have classes in your classification task. This is mainly for a classification task. And then you can classify and you can kind of train the whole system like this. So how exactly this happens, we'll see next. All right, so they make kind of analogies to the visual system and so on. We'll jump these. You can, everyone that does deep learning in some way is trying to make that. We're rather going to the specifics of how these capsules work and how their specific suggestions for them. Note that they say this is in no way the only implementation of capsules. It's just kind of an example to show how one could do it. All right. So first of all, they present their what you might call nonlinearity. So their nonlinearity, what it needs to do is, if you look at these capsule networks, the outputs here, the length of the outputs of these vectors, right, they're supposed to represent probabilities. And as such, they need to be, so here roof this door may be a vector like this, wall may be a vector like that. So initially, we simply specify the output is a vector. And in essence, these capsules are implemented in much the same way like your classic neural network layer would be implemented. So each of these capsules will be, in essence, a neural network layer by itself that outputs a vector. And there's nothing constraining the length of the vector initially. So their nonlinearity does constrain the vector to be of maximum length 1 and of minimum length 0. That's this nonlinearity here. So S here is the unscaled output of the capsule. And you can see here if the length of S gets close to 1, or gets really large, then this here becomes irrelevant. This whole term will be 1, and then the length of the final output of V here will be 1, right? So if this is very large, then the length of the scaled output will be 1. However, if the length is really small of the original output, so if this goes towards 0, then this becomes irrelevant, this becomes irrelevant, this will go towards 0, and the entire length will go towards 0. So this is kind of a nice way to scale these outputs, always to be between length 0 and 1. Then next thing is, so how this I find the most complicated part, right? So we'll jump ahead actually to how a capsules network is implemented. And this is the capsule network they implement. So first, it's an MNIST classifier. You have an MNIST image here, and it first goes through a simple convolutional layer. That's nothing new. This is a classic convolutional layer. There's 256 channels. It has a 9x9 filters and stride 1, so it will output a 20 by 20 time by 256 tensor. Then each of the outputs here is sent to each of these capsules, and now they're convolutional capsules, so that makes it a bit more complicated. But don't worry primarily about them being convolutional capsules. The analogy is exactly as in a classic neural network. You can implement these capsules as feed-forward capsules or as convolutional capsules, and well, maybe also as transformer capsules. I don't think anyone's done that. All right, there's a paper for you. So you'll send the output of this convolutional layer to each capsule, and then you have basically just 2 layers of capsules here. The first layer consists of 32 what they call primary caps. These 32 capsules each will output an 8-dimensional vector. And I'm simplifying here. It's convolutional, but they will, just for simplicity, they will each output an 8-dimensional vector, right? And these are exactly as we said before. So each of these will be responsible ultimately for a given entity or part of entity being there. Like in MNIST, this could be, is there a little curve on the bottom left side, right? This might indicate the presence of a 6 or an 8, something like this. And then these capsules here they're represented as rows. So each of these rows here is a capsule. And we have 10 of these. And these are simply your final classification capsules. So each capsule is responsible for indicating the presence or absence of one particular class of digits. So this will be of a 1, of a 2, of a 3, of a 4, and so on. Of a 0, I guess, somewhere as well. So these are 10 capsules. And the question is, how does information go from a capsule here, from the output of a capsule here, to any of capsule here? And the easy way to do this is simply to say, as in a classical neural network, the output here simply goes to the input here. Just you just put it there, basically unchanged. Now there's a bit of an issue here with the dimensions, but you can simply say, well, we simply put a weight matrix in to route to the capsules. But the idea of these capsules and this paper is to say, wait, these capsules, actually, we want to make them decide to which capsule in the next layer will they send their input, right? So the capsules can kind of decide where they want to send their output to. Like where is the capsule that detects maybe this one detects, is there a line in the right side of the image, right? Indicating maybe a 7 or a 1. This is probably most relevant for the 1 class and for the 7 class. So it might decide to route its output there. And the idea of how this routing happens is basically the topic of this paper. So the capsules route their output to the appropriate next layers capsules. How's this done? All right, this is done via what's called the routing mechanism. Now, I find it quite poorly described here, so I will simply draw it. I will simply try to make it up. All right, so we have capsules, and as I've drawn them before, right, we have 1, 2, 3 capsules, and we maybe have 2 parent capsules. Each of these capsules here will output a vector, as we said, and we'll only do it for this vector here. So this will output this vector, and it needs to decide where to here or to here do I send to this output. Now, what it does is there is an iterative procedure that has multiple steps. And this is, I think, this is at least the way I understand it. I think the important part to understand is that if we forward pass data through this network, it actually doesn't go forward in a straight line. What it actually does is it goes through a layer, and then it does multiple steps in between layers until it has decided where it wants to go in the next layer, and then it goes on to the next layer. And if there's another capsule layers, it does again multiple steps before it goes on. So that's my take on it. And the multiple steps are as follows. First, I'll send my output vector to all of the layers, like equally, all of the parent capsules. And so will everyone else, right? Everyone will send theirs equally to the parent. Now this isn't just done, and this may be here, this isn't just done just by sending it, but this is actually done by modulation of weight matrices. So each thing here, if this is capsule I and this is capsule J, there's a weight matrix in between, Wij, that is learned, right? This is a static weight matrix, and each one of these red arrows you see here has such a weight matrix attached to it. So each line you see here is actually modulated by such a weight matrix. So there's a quadratic number of these weight matrices flying around, and this will also then allow you that maybe this vector is 8-dimensional, but the input vector here is 16-dimensional, what we saw before. All right, so the input of capsule J here, it will receive, let's see what it receives. It will receive the output of capsule 1, V1, modulated by the, let's call this J, modulated by 1J, W1J. And it will also receive, this is a set, the output of capsule 2, modulated by the weight matrix for capsule 2, and so on. Now, what it does is it adds these all up into a softmax. So, let's write this. So it will add those all up, in a softmax weighted fashion. So it will actually compute a weighted average of those. Now the weights at the beginning are just 1, because it gets from each lower capsule it gets equal amount of this vector. But then this will give you an output. So this will give you some output. Let's put this in green. This will give you an output that's, I don't know how they call it in the paper. Let's just call it OJ. Right? And then what you do is, all right, you compare how much do each of the individual contributions agree with OJ. So you actually compute for each of these, you would compute the inner product. So you would compute the inner product of W1JV1 with OJ. And you would compute the inner product of W2JV2 with OJ. All right, the inner product. And then these inner products here will become the weighting coefficients for the softmax in the next iteration. Right. So this is a bit convoluted, but ultimately what you're saying is, if you're a capsule here, you'll send your output forward. You have an output, you send it forward, right, to the other capsule, and the other capsule will. So this is your output, and we'll forget about this weight matrices for now. This is your output. The other capsule will output its own output computed from the lower layers. Now we do an iteration again. If your output now aligns with this, you will send more of it. And these two that I've drawn here actually align pretty well, right? So you'll send more of it. You send more, right? And now maybe the output, the next computed output of the same capsule will be even more in that direction because you've contributed more, right? You'll send more, and then you're like in the next iteration, wow, these two are really equal. Sorry, this should be red here. Yours just keeps being the same. And then you say, well, I'm going to send even more to that one, right? Whereas another capsule whose initial output was basically like this, it will by itself compute the inner product with the original, it will send it here, right? It will compute the inner product with the original output. And it will realize, well, these do not align very much, and then it will send less, right? It will send less to the next step. And because it sends less in the next step, of course, the output will then probably align even less with that vector, and then it will send less and less and less. So this is called dynamic routing. The idea behind it is kind of that you route by agreement. So you will route to the parent capsules that agree with your output, and by agreement we mean kind of the inner product is high after modulating by this weight matrix. And that that basically means this weight matrix is responsible for deciding which information is relevant together. Whenever you have two vectors that align in the same layer, then in the sense of the capsule networks, those represent the same kind of information. And those will be routed together to the same capsule. In terms of the examples we made, maybe if a door and a roof is present, then these weight matrices that connect door and roof to the house class, they will transform a high vector in door and roof into aligning vectors for the house class, and thereby saying, look, these two, if I look at a door and a roof through the perspective of trying to be a house, right, then they are in much agreement on the presence of a house. So if I am a house, right, I am a house, and I look at a door, and I look at a roof through the kind of from the perspective of being a house, right? This is what these weight matrices do. They always have a perspective of the parent capsule. Then these two things, they make a lot of sense together. And thus I will route them to the same place, so they can both contribute to there being a house. Now, from the perspective of a house, if I look at a little beach with a tree on it, right, then that is not the same. That is not the same information as a door or a roof. So I will not route this to the house in the same strength. That is sort of the best way I have of explaining it, how these capsules work. Basically, the lower entities will always be routed for the relevance of the higher entities that are trying to combine the lower entities. If that wasn't, it's not entirely clear to me either yet, but it's the best shot I can give. The routing is here formalized. I find it hard to follow. The important thing is that there is an inner loop in all of this. So there is an inner iteration. And this inner iteration is computed in every forward pass. And so this routing where the information goes in the next layer, that is only the prior probability for that is learned, but the actual routing coefficients, those are dynamically computed in every forward pass. So every forward pass goes, information goes through a layer, then it goes multiple steps between two layers until it decides exactly what the distribution for the next layer is. And then the next layer computes its outputs, and that goes again multiple steps between these layers and the next layer. So that's the basic thing to remember. There's also some normalization involved. The squash is the nonlinearity we discussed. So what do they actually train now? At the end here, they have these 10 capsules, and each capsule will be responsible for recognizing the presence of one digit in the MNIST dataset, of course. And so what they do is they take the length of these vectors that are output by these capsules. These capsules are feed-forward capsules as opposed to the convolutional capsules here. So the feed-forward capsules output, again, a vector. The length of this vector is taken, and then it's basically trained like you would train a regression problem. And the loss here is specified up here. So if the image actually does contain this, if the training label actually has this digit present, this t here encodes that. So if k, let's say k is 2, right? So if k2, if there is a 2 in the image, and we know that because it's a training image, then the length of the output of capsule number 2 should be high. And this simply encodes that it should be very close to this m plus. And m plus here is, I think they set it to 0.9. So they say the length should be as close as possible to 0.9. Whereas if the 2 is not present, then tk will be 0. Then this part will be active, so it's only one of these two parts will be active. Then the length of the vector, so of capsule number 2, should be close to this m negative, which is 0.1. It's basically a regression problem saying if the given entity is in the image, then please make the length as close as possible to 0.9, and if it's not, make it as close as possible to 0.1. So this is a classic, let's say, regression loss on the length of the output vectors. The lambda is just a factor to dampen the contribution for all the negative classes with respect to the one positive class, of course, per capsule. It turns out this is actually not enough So this will be the classification output, but it seems not enough. They don't say it's not enough, but they simply say we additionally do the following. So what they also do is they introduce a reconstruction loss. Now, if this model is trained correctly, then these capsules here, these last capsules, especially this one, maybe that's the capsule corresponding to the class of the digit 8, will not only encode if an 8 is there or not, as in the length of the vector output, but it will also encode the properties of the 8. It is a 16-dimensional vector, so it will encode, hopefully, things like the stroke width. So width. Then it might encode the maybe the rotation of the digit. Then it might be controlled the tightness of the loop. So I can have an 8 with very large loops, or I can have an 8. Oh, sorry, this is a smaller 8. I can have an 8 with very tight loops. So it might, encode things like this. So technically, it will be possible to reconstruct from this description. Say, the width is high, the rotation is 0, and the tightness is low. Then maybe I have a wide, widely stroked, not tight 8 that is not rotated. Right, so it should be possible to reconstruct this, and they do exactly that. So they take this last capsule of the class that is the actual training label, that's called the reconstruction target, and they feed this to a simple feed-forward neural network that at the end, you see this is exactly the MNIST size, will try to reconstruct the image. So if the image here, if this image goes in, then it goes all through here. It will take the class 4 here, feed it through this network, reshape it to an image again, and hopefully what will come out is again this 4 here. And it will then have an auxiliary loss in addition to the loss of this classification loss here, well, auxiliary loss that tries to reconstruct the original image. Right, and that's simply I believe it's just an L2 reconstruction loss that is scaled down, that it doesn't dominate. So they also train the network basically to reconstruct this, and I believe they do this because the length isn't quite enough to make it do what they want it to do. Thus, they by having this reconstruction here, they really kind of enforce that the individual capsules, the individual dimensions, must encode some kind of information about the original image. And since the original images in the MNIST dataset at least vary by those things, by stroke width, by rotation, by tightness, that by this loss will be reflected in the reconstruction. All right, so how are they doing? Here you see different examples of inputs and then reconstructed outputs. And this, seems pretty good actually. So you see here all of these. The input image is reconstructed fairly well. So the numbers up here mean the following. So on the right are the failure cases. Here, the input image is a 5 labeled in the training data, but the network actually classifies it as a 3. But then now you have two choices, right? This is the same sample. Now you have two choices for reconstruction. Either you reconstruct the capsule that is actually is the true capsule that should be activated, and you reconstruct from that, or you reconstruct from the capsule that the network says it classifies it as. So here it mixed up a 5 for a 3. If you still take the 5, the capsule, and reconstruct it, you see it actually looks like the original image, but it looks much more like a 5. And if you take the 3 capsule to reconstruct, which is what the network classified this as, it looks like the original image, but it looks much more like an actual 3, right? It's missing the part up here, whereas over here it's missing this part here. So the network really seems to kind of learn the different variations of these digits, and in an ambiguous case such as this one, it can actually go either way, and it can actually reconstruct the original output in either interpretation. So once as a 3 and once as a 5. It would be interesting to see what the actual length of the vector of both of these classes were that were mixed up. And here they compare their accuracies. So they have a baseline model, which I believe is just like a CNN, where they get a decent kind of error, and then the capsule networks, they get a lower error. And here you see, as you add the reconstruction loss and as you add routing more, so one step of routing simply means the first step is where you send your output equally to each parent. That is as in the classical neural network case. But if you introduce 3 steps of routing, then your error drops even lower. So they kind of are on par with baseline CNNs on MNIST here. They also explore what their capsules learn. So as I said, the individual capsules, the dimensions should encode kind of properties of the variations of the class samples. And here they explore this in the different capsules. So they change some dimensions and they run it through their reconstruction networks, and indeed they discover that there's like a scale and thickness dimension, stroke thickness dimension, there's a skew dimension, and so on, width and translation. So that this is pretty remarkable. These networks really, if you train them in this way, they really seem to learn about the entities and about the properties of the entities, and that seems to be quite interesting. You see that there's everything here stays well within the class that the capsule is assigned to. They also, there's robustness to affine transformations where they improve over the baseline. It's kind of an auxiliary experiment. The next interesting experiment is what they call the MultiMNIST experiment. The MultiMNIST experiment is done by taking 2 different MNIST digits and basically just overlapping them. So they have, shift them slightly, but as you see here or here, they are overlapped heavily. And the task of the network is to figure out which 2 overlapping digits are in the image. And the network is very, very good at doing this. The capsule network, that is, and better than the baselines, because the capsule network simply encodes the presence and properties of a particular instance in the image. If you simply take the top 2 length capsules and then reconstruct those independently, then you can basically segment the image, and you see this here. So the different colorations come from 2 different reconstructions of the image from 2 different capsules. So green is from one capsule and red from the other capsule. So the network correctly identifies that it's a 6 and a 0, right? And it also correctly identifies not only which pixels belong to the 6 and which belong to the 0, but also pixels that belong to both. So that's not a problem if you use capsule networks as they are. And notable to say here, the way they train is they train the actual reconstruction by only reconstructing one at a time. So the kind of the premise of the dataset is that you actually have access to the underlying individual digits while training. So like the images of the individual digits. You don't only have this label here, but that's a detail. Here are some kind of failure cases where it misclassified or you misspecify the capsules, and it's kind of unable. Here you see to assign the digits of the misclassified or the pixels of the misclassified thing It's quite interesting to look at the failure cases, but I find it more interesting to look at actually the success cases and the kind of ease at which the capsule networks can do this simply by how they're structured. All right, so then lastly, they also experiment on CFAR10, and interestingly, the CFAR10 experiments show that the capsule networks don't perform as well there. And as you know, CFAR10 is a data set that is about the same size as MNIST, but it's first of all color, and second of all, it's natural images, and so they have quite a bit of clutters. It's not black and white, black background, white digits. It's actually, there's a sky like on an image. There's lots of things going on, and right, there's a tree, and there's stuff here, and there's stuff here. And the capsule networks, they like to account for things in the image. So they like to have a capsule corresponding to everything that's going on here, and here, and here, and here, and here. And if the whole background is black, that is not a problem. You can account for simply the background. But if there's lots of things going on, then these capsule networks get they get a bit over-explanatory. They want to explain everything, and that degrades the performance. Now, this paper basically says, yeah, you can have something like a none of the above category, and they found that it helped to introduce that. In my opinion, that I think the solution will be more towards introduction of a better loss function for this, because like such that you don't need kind of to explain the entire thing. Rather than here what you do is you simply explain it by saying it's none of the above, but it's incredibly hard to balance that, my opinion. Yeah. All right, so that is basically the end of this. They say they have a discussion here where they compare capsules against other related work. But I hope that you kind of got an overview of how this works now, and as much as possible. And with that, that was it from me. Thanks for watching. Bye bye.